Step 2 in the process of this section is to start taking trig expressions and setting them equal to each other. And I think one of the things that we have to realize here is equality and identity are essentially interchangeable. And so what we're going to be doing is relying on our base fundamental identities to help develop other equalities, which we call identities, or checking out other identities that other people have come up with. And I think it was stated earlier in the first presentation that there is an infinite amount of identities, and so we can't just sit and fill our toolbox with every one of these. We have to have the ability to prove that these are true so that we can use them. Or we have to use the ability we learned in our last presentation of simplifying trig expressions so that we can develop our own identities. First off, just because it's written as an equation doesn't mean it's an identity. Sine of x plus cosine of x equaling 1 is not an identity. And we could show that real quick because we learned in geometry the easiest way to disprove something is to come up with one counterexample. And so let's find a value for x that makes this false. And I think we can take any value along our unit circle. So let's just try pi over 4. Nice easy one to work with. So you got the sine of pi over 4 plus the cosine of pi over 4. And let's evaluate. I picked that because both the sine and cosine of that is square root of 2 over square root of 2. Square root of 2 plus square root of 2 is 2 square roots of 2 over 2, which is just the square root of 2, which does not equal 1. And so an easy way to disprove an identity, or a possible identity would be the way to say it, is to check a value of the variable and find something that makes it false. Now the other thing that we should have from our geometry days is how to prove something true. If something's true, it has to be true for every possible part of the domain. So every value I put in for x has to make that true. And so how do you prove that every value makes it true? Well, that's what we're going to do right now, is learn a process of proving identities where we're going to take one side of the equation and manipulate it, change it around, use our fundamental identities to transform it into the other side of the equation. The general steps for this, and I say general steps because there's not a single one of these that are identical. There's a lot of different techniques we're going to use. I'm going to go through 4 examples to show you different types of techniques that you may use to prove triangle identities, or not triangle identities, I guess trig identities. But it is pretty tough at first until you start seeing some of the tricks that get used over and over. We typically start with one side and work with that side and try to set it equal to the other. And the way we determine what side to work on is take the more complicated side. It's easier to work around with. There's more things going on, more possibilities of using our identities. And use your known identities. The number one that we want to look for is our Pythagorean identities, because we can replace a big chunk with 1. If we find sine squared plus cosine squared anywhere, we can replace that with 1. And that sure is a big help in terms of simplifying. And if at some point you're stuck and not sure where to go, convert to sines and cosines. Convert to something that we're familiar with and comfortable with, and try and limit the number of variables you have. Now typically you'll see a question like this. So it starts off with cosine of x times the quantity secant x minus cosine x. And there's our equality right here. So equalities are identities. And so what's on the left equals sine squared theta. And so this is something that someone else has come up with, and we have to verify it or prove that it's true. To me, this seems to be more complicated. There's several operations going on. I see a set of parentheses. So let's start off working over here. Where do you start off? Well, I guess the one thing that I notice here is I see two cosines and a secant. And the first thing I remember is that secant is the reciprocal of cosine x. So let's go in and rewrite that secant as 1 over cosine. And we're going to keep my equal sign. One of the things when you work with identities, always keep your equal signs lined up. Hopefully we could take the left side of the equation and at some point transform it into the right side of the equation. So parentheses scream distributive property. And so when you distribute here, you end up with cosine x over cosine x minus cosine times cosine as cosine squared x. There's my equal sign. And now cosine x over cosine x is 1 minus cosine squared x. And so right here, 1 minus cosine squared x, that is a form of our Pythagorean identity, which is sine squared x. And so now what we have is left-hand side equals our right-hand side, and so we're done. Except that looks like a 7 there. Let's do this right. Let's make it look good. Sine squared x equals sine squared x. Oh, just notice that. This right here, some of you are probably wondering the whole gamut here, what's going on. But that right there should have been an x. I tried to erase it there too. Doing some learning here. Alright, I don't know why I put theta in there originally. Hopefully that doesn't cause too much confusion. Mistake on my part. Alright. Verify 2 times the tangent of x times the secant of x equals this subtraction over here. And as I'm looking at this, right side is sticking out like a sore thumb. Work with me, work with me. Subtraction, addition tend to be more complicated. Think back working with irrational expressions. If I'm going to do this subtraction, I need a common denominator. And so my common denominator here, I'm going to move this equal sign over a little bit. My common denominator is going to be 1 minus the sine of x times 1 plus the sine of x. And both fractions need to get that, so I'm going to do that right away here. 1 plus the sine of x, 1 minus the sine of x. Now let's go and look at what happens in our numerators. All right, in the first fraction, our denominator already had 1 minus the sine of x, so we had to multiply by 1 plus the sine of x. And so that goes on in our numerator. Our numerator 1 times 1 plus the sine of x. Because we had to multiply by a form of 1. 1 plus the sine of x over 1 plus the sine of x is 1. So we didn't change the value of that fraction, we just changed its form. The second fraction here, we're going to do the same thing, except it's our numerator of 1 times 1 minus the sine of x. That is a parenthesis right there. And I don't know that I necessarily had to write these ones out there, but I'm just showing you that it's the numerator you started with times what we multiplied the denominator by. So I'm actually going to go in and erase those because that multiplication there is understood to be there anyway. So now let's combine this into one single fraction. Common denominator stays the same as the two fractions above. So I still have my 1 minus sine of x and 1 plus the sine of x. And now let's see what happens to my numerator. Alright, so on the left here, 1 plus the sine of x minus, now I got to distribute this negative sign here, minus sign. Minus 1 minus a negative sign is plus sine x. And look what happens here in the numerator. The 1 minus 1 cancels, and I'm left with sine x plus sine x, which is 2 times the sine of x. And that's kind of what I wanted here because, and then I still have my common denominator. Now when you look at the left-hand side, there's a 2 times tangent of x secant of x. So somehow I have to work my way from what I have here, 2 times the sine of x over this multiplication. But when I look at that multiplication, I see conjugates. And we like that in trig because the multiplication of this conjugates is 1 minus sine squared x, which once again is a form of our Pythagorean identity, which is equal to cosine squared x. And we have our 2 times the sine of x on top. Now remember what cosine squared x is. I can rewrite this whole thing as 2 times the sine of x over cosine of x times cosine of x. And so this whole expression right here can be rewritten as a series of 2 multiplications. 2 over 1 times sine x over cosine x times 1 over cosine x. And if you look at this, my numerator is still the 2 sine of x, and my denominator of this multiplication is cosine squared of x. So once again, I just changed the form, and when I go and finish this off, 2 over 1 is 2 times sine over cosine is tangent of x, and 1 over cosine of x is secant of x. And so there's a lot of work going on there. But I think the key there was realizing that we had an addition or subtraction of fractions. That's our complicated side. Let's get our common denominator and follow the algebra, which is what this whole chapter is about. So if you want to look at a couple more examples, I am going to make another presentation. It would be worth going through because I'm going to show you 2 other techniques that are useful in proving identities. Thank you.